Hey guys, welcome back. Tonight, we will be exploring one of the most bizarre and terrifying weather phenomena in the known universe. Planets, where it literally rains glass. You think Earth's weather can be extreme? You think you've seen storms that could kill you? Well, you're about to discover worlds where the very atmosphere becomes a weapon, where tiny shards of molten silicate fall from alien skies at supersonic speeds. These aren't just theoretical curiosities. They're real worlds that exist right now in our galaxy. Places where the laws of physics create conditions so extreme, they challenge everything we thought we knew about planetary atmospheres. Tonight, you're going to experience what it would be like to visit one of these glass rain worlds. And trust me, it's a journey that will change how you think about weather forever. If you like the content and want to support the channel, be sure to subscribe. You're standing in the observation deck of the research vessel Meridian, watching through reinforced viewing ports as your destination grows larger against the starfield. AD 189, 733b looms. Looms before you like a blue marble suspended in the cosmic void. Its azure surface swirled with bands of clouds that look deceptively Earth-like from this distance. But you know better. You've studied the atmospheric data, read the spectroscopic analyses, and understand exactly what those innocent-looking clouds contained. This isn't water vapor creating those beautiful blue swirls. It's vaporized glass. Silicate particles suspended in an atmosphere so violent that winds reach speeds of over 5,400 miles per hour. You feel your stomach tighten as the ship's atmospheric specialist, Dr. Sarah Martinez, joins you at the viewing port. Beautiful, isn't it? She says, her voice carrying a mixture of awe and apprehension. From here, you'd never guess that planet is literally hell-made manifest. Those clouds you're looking at are composed of silicon dioxide particles, essentially microscopic glass fragments suspended in hydrogen and helium at temperatures reaching 1800 degrees Fahrenheit. The science behind what you're seeing is both fascinating and terrifying. Tragedy 189, 733b is what astronomers call a hot Jupiter, a gas giant that orbits so close to its parent star that it completes a full year in just 2.2 Earth days. You try to wrap your mind around that concept. This entire world, larger than Jupiter, whips around its sun faster than you could drive across a continent. The tidal forces alone are staggering, with one side of the planet permanently facing the star, while the other exists in eternal darkness. The temperature differential between the day and night sides creates atmospheric dynamics unlike anything in our solar system. Dr. Martinez explains, as you watch the planet's rotation reveal the stark boundary between its illuminated and dark hemispheres. You're looking at temperature differences of over 1,000 degrees Fahrenheit between hemispheres, which drives winds that make Earth's most powerful hurricanes look like gentle breezes. You can see the Terminator line, the boundary between day and night, as a stark division across the planet's surface. On the day side, the atmosphere glows with the angry red-orange of superheated gas, while the night side appears as a darker blue, though still hellishly hot. Standards. It's along this boundary that the most extreme weather occurs, where the massive temperature differentials create the conditions for glass rain. Your ship's atmospheric probe specialist, Dr. James Chen, approaches with a tablet displaying real-time data from the advanced probes already deployed in the planet's atmosphere. The preliminary readings are even more extreme than we expected, he reports, his voice tight with a mixture of excitement and concern. Wind speeds at the Terminator line are measuring over 6,200 miles per hour. That's nearly twice the speed of sound on Earth. And the glass particle concentration. He pauses, checking his readings again. The atmosphere is essentially a sandblaster operating at supersonic speeds. You study the data on Dr. Chen's tablet, trying to comprehend the sheer violence of the atmospheric conditions you're preparing to study. The glass particles range in size from microscopic fragments smaller than dust to chunks nearly a centimeter across, all of them traveling at speeds that would turn them into deadly projectiles. You realize that even a particle the size of a grain of sand moving at these velocities would hit with the force of a bullet. How is this even possible? You ask, though you've studied the theoretical models. Hearing it explained while looking at the actual planet makes it feel more real. And more terrifying. Dr. Martinez pulls up a holographic display showing the planet's atmospheric dynamics. It starts with the extreme temperatures on the day side. She explains. Surface temperatures reach nearly 2,000 degrees Fahrenheit, hot enough to vaporize rock and metal. Silicon dioxide, essentially sand and glass, gets vaporized and lifted high into the atmosphere where it forms clouds, just like water vapor forms clouds on Earth. The holographic model shows the convection currents rising from the superheated day side, carrying vaporized silicates high into the atmosphere, where they begin to cool and condense. You can see how the extreme temperature differences create a circulation pattern that carries the glass vapor from the day side toward the cooler night side. But here's where it gets really interesting, Dr. Chen adds, manipulating the display to show wind patterns. The extreme temperature gradient between day and night creates these massive jet streams that flow around the planet at incredible speeds. As the glass vapor gets caught in these jets and moves toward the night side, it cools and condenses back into solid particle. You watch the simulation as tiny points of light represent glass particles forming in the cooling atmosphere, then getting caught up in the supersonic winds that flow around the planet. The particles grow larger as more vapor condenses onto them, creating what are essentially glass raindrops that fall through the atmosphere at terminal velocities that would be lethal to any spacecraft, not specifically designed to handle such conditions. The truly remarkable thing, Dr. Martinez continues, is that this process is happening continuously. This isn't weather that comes and goes. It's a permanent atmospheric feature. HD 189 733D has been raining glass for millions of years, possibly billions. The entire atmospheric cycle is based on the continuous vaporization and condensation of silicate materials. Your ship's captain, Elena Rodriguez, joins the group as the vessel begins its final approach to the planet's outer atmosphere. We'll be deploying our reinforced atmospheric probes in 30 minutes, she announces. The probes are designed to survive the glass rain for approximately 47 minutes before the particle bombardment degrades their systems beyond operational limits. 47 minutes. You feel a chill as you realize that's how long the most advanced material science Earth has to offer can survive in this environment. The probes are armored with diamond composite hulls and protected by electromagnetic deflector fields, yet they're expected to be destroyed in less than an hour by falling glass. As your ship moves closer to HD, 189,733 b. You begin to see more detail in the planet's atmospheric structure. What looked like uniform cloud bands from a distance resolve into incredibly complex storm systems with features that dwarf anything in Earth's atmosphere. You can see spiral formations that would span multiple continents, bands of different colored clouds that indicate varying particle densities and compositions, and lightning displays that flash continuously across the planet's surface. Those lightning bolts you're seeing are different from Earth lightning, Dr. Chen explains, noticing your attention to the electrical activity. They're created by the friction of glass particles moving through the atmosphere at high speeds. The electrical discharges are so powerful they can be detected from interstellar distances. In fact, that's one of the ways we identify planets with glass rain. The distinctive radio signature of their atmospheric electrical activity. The concept of lightning created by falling glass particles adds another layer of danger to this already hostile world. You imagine the electromagnetic pulses generated by continuous electrical storms spanning an entire planet, powerful enough to disrupt electronics from millions of miles away. Any spacecraft trying to operate in this environment would face not just the physical danger of glass particle bombardment, but also the constant threat of electrical systems being fried by atmospheric discharge. Your ship's atmospheric entry specialist begins the final systems check for deployment. All probes show green across the board, she reports. Diamond hull integrity at 100%, electromagnetic shielding online. All scientific instruments calibrated and ready. We're as prepared as we're going to be for what's waiting down there. You feel the subtle vibration through the ship's hull as the first atmospheric probe launches, beginning its descent toward HD 189,733b's violent atmosphere. On the main display screen, you can see telemetry from the probe as it approaches the outer atmospheric layers, its sensors already detecting the first traces of silicon dioxide particles suspended in the superheated gas. Entry in 10 seconds, the specialist announces. Probe 1 crossing the atmospheric boundary. Now, immediately, the probe's exterior camera feeds show a transformation that takes your breath away. What had been the black of space suddenly becomes a hellish orange-red glow as the probe enters the planet's upper atmosphere. The camera shakes violently as the first glass particles impact the probe's hull, creating a continuous drumming sound that comes through the audio feeds. Initial particle impact rate, 300 strikes per second, Dr. Chen reports, monitoring the probe's structural sensors. Hull integrity, holding at 97%. Atmospheric temperature, 1650 degrees Fahrenheit, and climbing. You watch in fascination and horror as the probe's cameras show the glass rain in all its terrible beauty. The particles appear as streaks of light against the glowing atmospheric background, some tiny as dust motes, others large enough to be clearly visible as individual fragments. They fall in sheets and waves, driven by winds so powerful that they move horizontally as much as vertically. Look at the size variation, Dr. Martinez points out, highlighting different particles on the display. You've got everything from microscopic dust to chunks nearly an inch across, all moving at supersonic speeds. It's like being inside a blender filled with broken glass while someone shakes it at 6,000 miles per hour. The probe continues its descent, and you begin to see the full complexity of the glass rain phenomenon. The particles don't fall uniformly. They form patterns and streams, creating what looks almost like curtains or veils of falling glass that shift and move with the atmospheric currents. Some areas are dense with particles, while others are relatively clear, creating a constantly changing landscape of glass precipitation. We're seeing distinct layers of particle density, Dr. Chen observes, analyzing the incoming data. It appears that different atmospheric altitudes have different concentrations and sizes of glass particles. The larger chunks seem to form at higher altitudes, where there's more time for vapor to condense, while the smaller particles dominate the lower atmosphere. As the probe descends deeper into the atmosphere, the external temperature continues to climb, and you can see the glass particles beginning to glow with their own heat. At these temperatures, the boundary between solid and liquid becomes blurred. Some particles appear to be partially molten, creating streaks of liquid glass that fall like fiery rain. Temperature now at 1850 degrees Fahrenheit. The specialist reports, "We're approaching the probe's maximum thermal tolerance, hull temperature rising toward critical levels." You realize you're witnessing something that no human has ever seen before. The actual process of glass formation and precipitation in an alien atmosphere. The particles you're watching form from vaporized rock and sand, condense in the upper atmosphere, and fall as literal glass rain through temperatures hot enough to melt copper. It's a weather phenomenon that exists nowhere else in our solar system. A unique consequence of the extreme conditions on worlds orbiting very close to their parent stars. The probe's spectrometric analysis begins providing detailed information about the composition of the glass particles. We're seeing primarily silicon dioxide as expected, Dr. Martinez reports, but there are also significant concentrations of aluminum oxide, magnesium oxide, and iron comes. This isn't just window glass falling from the sky. It's a complex mixture of different silicate minerals, each with different melting point. You study the spectral analysis data, realizing that the glass rain on HD 189,733b is far more complex than simple silica precipitation. The different mineral components create glass particles with varying colors, densities, and properties. Some particles appear blue-green from copper compounds. Others show the deep red of iron oxides, and still others flash with the metallic gleam of aluminum-rich glass. It's like a cosmic stained glass window that's been shattered and is falling from the sky. You murmur, struck by the bizarre beauty of the phenomenon despite its deadly nature. The probe's cameras capture images of glass particles colliding with each other in mid-atmosphere, creating brilliant flashes of light as fragments shatter and reform. The continuous particle interactions create a dynamic, ever-changing display that would be beautiful if it weren't so incredibly dangerous. You realize that the atmosphere of HD 189,733b is essentially a continuous glass storm that has been raging for geological ages. Hull integrity down to 85%. The specialist reports as the probe continues its descent. We're taking significant particle impacts. The diamond composite is holding, but we're seeing microfractures beginning to form. Estimated survival time, 32 minutes remaining. The countdown to probe destruction adds urgency to the scientific observations. Every minute of data gathered from this hostile environment represents information that couldn't be obtained any other way. You're not just watching a weather phenomenon. You're witnessing the limits of human technology pushed against one of the most extreme environments in the known universe. As the probe reaches the denser atmospheric layers, the glass rain becomes even more intense. The camera feeds show what can only be described as glass blizzard conditions. Particle density so high that visibility drops to just a few meters. The continuous impacts create a sound like continuous machine gun fire. Transmitted through the probe's hull to its internal microphones. "This is incredible," Dr. Chen says, reviewing the particle impact data. "We're measuring impact velocities of over 4,000 miles per hour. These particles are hitting with enough force to penetrate solid steel. It's no wonder that no natural materials could survive long-term exposure to these conditions." You try to imagine what it would be like to experience this glass storm firsthand, then immediately push the thought away. The human body wouldn't survive even microseconds of exposure to these conditions. The combination of extreme heat, supersonic particle impacts, and crushing atmospheric pressure would destroy any known form of life instantly. The probe's atmospheric analysis reveals more surprising details about the glass rain environment. We're detecting electromagnetic fields created by the charged glass particles, Dr. Martinez reports. The friction of all of these particles moving through the atmosphere is creating a continuous static electrical field that spans the entire planet. It's like the world's largest Van de Graaff generator. And this electrical activity explains the continuous lightning displays visible from space. The entire atmosphere of HD 189-1733b is essentially a massive electrical storm powered by falling glass particles. The electromagnetic environment would be hostile to any electronic equipment, creating another layer of danger for any spacecraft attempting to operate in the planet's atmosphere. "Look at this," Dr. Chen calls out, highlighting a particularly dense stream of particles on the display. "We're seeing what appears to be organized flow patterns in the glass rain. The particles aren't falling randomly. They're following specific atmospheric currents that create rivers and streams of glass moving through the atmosphere." You can see what he means. Distinct channels of dense particle flow that snake through the atmosphere like aerial rivers made of falling glass. These streams appear to be guided by temperature gradients and pressure differences, creating a complex three-dimensional topology of glass precipitation that changes continuously as atmospheric conditions shift. The probe's descent continues, and you begin to see evidence of the glass rain's interaction with the planet's atmospheric chemistry. We're detecting chemical reactions occurring between the glass particles and the atmospheric gases, Dr. Martinez observes. At these temperatures and pressures, the silicon dioxide is reacting with hydrogen to form silane compounds. The atmosphere isn't just carrying glass particles. It's actively modifying their chemical composition as they fall. This chemical activity adds another dimension to the glass rain phenomenon. The particles aren't just falling passively through the atmosphere. They're undergoing continuous chemical transformation, creating new compounds and releasing gases that further modify the atmospheric composition. PD 189. 33B's atmosphere is essentially a giant chemical reactor powered by the continuous cycle of glass vaporization and condensation. Hull integrity now at 70%. The specialist reports, "We're seeing significant erosion of the diamond composite from particle impacts. The electromagnetic shielding is also being degraded by the continuous electrical activity. Estimated survival time, 19 minutes. The probe is literally being sandblasted to death by the glass rain. despite being protected by the most advanced materials available to human technology. You realize that this demonstrates the incredible power of the atmospheric forces at work on HD 189, 1733, ... The continuous particle bombardment is slowly grinding away even diamond-hard protective materials. As the probe reaches the deepest atmospheric layers, it will survive. The environmental conditions become even more extreme. Temperature now exceeding 2,000 degrees Fahrenheit. Dr. Chen reports. At this temperature, many of the glass particles are becoming partially molten. We're essentially seeing liquid glass rain. The camera feeds show an otherworldly scene of glowing, semi-liquid particles falling through the superheated atmosphere. Some particles appear to be completely molten, forming droplets of liquid glass that fall like fiery raindrops. Others are partially solid with molten cores, creating unique formations, unlike anything possible in Earth's atmosphere. This is remarkable, Doctor. Martinez says, studying the thermal imaging data. We're seeing glass particles that are molten on the outside, but solid on the inside, creating hollow glass spheres that form as they fall. It's like the atmosphere is creating its own glass beads through natural processes. The formation of hollow glass spheres adds another fascinating aspect to the glass rain phenomenon. You realize that HD 189,733b's atmosphere is essentially a natural glass factory, continuously creating complex glass structures through processes that involve extreme temperatures, supersonic winds, and chemical reactions that couldn't occur anywhere else in the known universe. The probe's final minutes of operation provide the most dramatic footage of the entire mission. As its hull integrity continues to degrade, the internal cameras begin showing the effects of glass particle penetration. Tiny fragments of glass begin appearing inside the probe's protective shell, glowing red-hot from their passage through the superheated hull material. Hull breach detected, the specialist announces. Glass particles are penetrating the diamond composite, internal temperature rising rapidly. We're losing system integrity across multiple platforms. You watch in fascination as the probe's internal systems begin to fail under the assault of glass particles that have managed to penetrate its supposedly impregnable defenses. The particles, still moving at incredible velocities, ricochet around the probe's interior like tiny bullets, striking sensitive equipment and causing cascading system failures. We're getting data right up until the end, Dr. Chen reports. The probe is transmitting atmospheric composition, temperature, pressure, and particle impact data even as it's being destroyed. This is incredible scientific information. We're literally watching the destruction process from the inside. The final camera feeds show the probe's interior being gradually filled with glowing glass particles as more and more of the hull is breached. The electronic systems spark and fail as the particles impact sensitive components. But the probe continues transmitting data until the very moment its communication systems are destroyed. Signal lost, the specialist reports. Probe 1 has been destroyed by atmospheric conditions. 41 minutes, 18 seconds. All scientific objectives achieved. The silence that follows the probe's destruction is sobering. You've just witnessed the complete annihilation of one of humanity's most advanced technological achievements by the natural forces of an alien world. The glass rain of HD 189,1733 has claimed another victim adding the remains of your probe to the countless tons of debris that must litter the planet's deeper atmospheric layers. The data we collected will revolutionize our understanding of extreme atmospheric dynamics. Dr. Martinez says, breaking the silence. We've documented glass rain formation and precipitation in real time, measured particle velocities and compositions, and observed chemical reactions that don't occur anywhere else in the universe. This mission represents a major breakthrough in exoplanetary atmospheric science. You begin to appreciate the broader implications of what you've witnessed. HD 189,733 isn't just an interesting curiosity. It's a natural laboratory for studying physical and chemical processes under extreme conditions. The glass rain phenomenon demonstrates atmospheric dynamics that push the boundaries of current scientific understanding and provide insights into the behavior of matter under conditions that can't be replicated in Earth-based laboratories. There are probably thousands of worlds like this in our galaxy, Dr. Chen observes. Hot Jupiters with glass rain, metal snow, ruby storms, and weather phenomena we haven't even imagined yet. Each one represents a unique set of physical conditions that can teach us something new about how matter and energy interact under extreme circumstances. The thought of thousands of glass rain worlds scattered throughout the galaxy is both exciting and humbling. You realize that HD 189,733b represents just one example of the incredible diversity of atmospheric conditions that exist on exoplanets. Each world with its own unique combination of temperature, pressure, chemical composition, and stellar radiation creates its own distinctive weather patterns and phenomena. We're preparing to deploy Probe 2, Captain Rodriguez announces. Based on the data from the first probe, we've modified the descent profile to maximize time spent in the most scientifically interesting atmospheric layers. We should be able to gather additional data on glass particle formation and the chemical processes occurring in the upper atmosphere. You feel a mixture of anticipation and apprehension as the second probe is prepared for launch. The first probe's destruction was sobering, but the scientific data it provided was invaluable. Each probe that ventures into HD 189,733b's hellish atmosphere adds to humanity's understanding of one of the most extreme weather phenomena in the known universe. The second probe launches and begins its descent toward the glass rainstorms of HD 189,1733b, carrying with it the hopes of advancing human knowledge about the strange science of worlds where the very atmosphere becomes a weapon. You know that this probe, like the first, will be destroyed by the hostile conditions it's designed to study. But in its destruction, it will provide insights into atmospheric physics and chemistry that couldn't be obtained any other way. As you watch the telemetry from Probe 2, beginning to show the first signs of atmospheric entry, you realize that your journey to understand the glass rain worlds is far from over. The data collected from these probes will take months or even years to fully analyze, and each new insight will likely raise new questions about the complex interactions between extreme weather phenomena, atmospheric chemistry, and extreme weather phenomena. The universe is vast and filled with wonders that challenge human understanding and push the boundaries of what we think is possible. Glass rain worlds like HD 189,733 represent just the beginning of our exploration into the strange science of exoplanetary atmospheres. Each new discovery opens doors to new questions, new theories, and new possibilities for understanding the incredible diversity of conditions that exist among the stars. Your mission continues, but the story of glass rain planets is just beginning. You watch intently as Probe 2 begins transmitting data from HD 189-733b's upper atmosphere. Its sensors immediately detecting conditions that are even more extreme than the first probe encountered. The particle density readings show a massive glass storm system moving across the Terminator line, with wind speeds exceeding 7,000 miles per hour and glass fragments ranging from microscopic dust to chunks the size of hailstones. "We're seeing something unprecedented," Dr. Martinez announces, her voice tight with excitement and concern. "The atmospheric dynamics have shifted significantly since our first probe. There appears to be a massive storm front moving through the region, essentially a hurricane made of glass particles and superheated gas that spans half the planet." The implications hit you immediately. You're not just observing static weather conditions, you're witnessing HD 189,733b's atmosphere in a state of active violent change. The glass rain you observed from the first probe was apparently just the baseline condition. Now you're seeing what happens when this already extreme world experiences what passes for severe weather in its hellish environment. "Look at the temperature readings," Dr. Chen calls out, pointing to his displays. "The storm front is driving temperatures even higher. We're seeing spikes up to 2,200 degrees Fahrenheit. At those temperatures, even iron would be glowing red hot. The glass particles aren't just raining down. They're being superheated to the point where they're emitting their own light." Okay, well, you can see this phenomenon clearly in the probe's camera feeds. What had been streams of falling glass particles are now rivers of glowing, incandescent fragments that light up the atmosphere like falling stars. The entire visible spectrum is represented in the light show. Blue-white particles of pure silica, green streaks from copper-contaminated glass, red glows from iron-rich fragments, and a really dry. It's like watching the aurora borealis, but made of molten glass falling at supersonic speeds. You murmur, mesmerized by the deadly beauty of the display. The probe's atmospheric analysis reveals that the storm is creating chemical conditions unlike anything observed in the first deployment. We're detecting the formation of exotic glass compounds, Dr. Martinez reports. The extreme temperatures and pressures in the storm are forcing silicon dioxide to combine with other atmospheric components in ways we've never seen before. We're essentially watching the creation of entirely new types of glass that don't exist anywhere else in the universe. This discovery adds another layer to the scientific significance of your mission. HD 189,733b isn't just a world with extreme weather. It's a natural laboratory for creating materials that couldn't be produced under any other conditions. The glass particles falling through its atmosphere represent compositions and structures that could have applications in advanced materials science if they could somehow be studied and replicated. The electromagnetic activity is off the charts, Dr. Chen adds, monitoring the probe's electrical sensors. The friction of all these superheated glass particles is creating electrical fields strong enough to power entire cities. We're seeing lightning bolts that would dwarf anything in Earth's atmosphere. Some of these electrical discharges are over 100 miles long. You watch in awe as the probe's cameras capture massive lightning bolts arcing between glass particle clouds. each discharge bright enough to temporarily overload the camera's sensors. The lightning isn't the familiar blue-white of Earth's electrical storms. It flashes in colors determined by the metallic content of the glass particles, creating rainbow displays of electrical activity that span the entire visible horizon. Hull integrity at 92% and falling rapidly. The probe specialist reports the increased particle density and velocity are accelerating the erosion rate. We're taking impacts at nearly twice the rate of the first probe. Estimated survival time has dropped to 31 minutes. The race against time adds urgency to every observation. You realize that you're witnessing phenomena that may never be observed again. The specific storm conditions creating these extreme glass rain effects might not occur again for years or decades. Every minute of data collected represents irreplaceable scientific information about one of the universe's most violent weather systems. As the probe descends deeper into the storm, the glass rain becomes increasingly surreal. The camera feeds show what can only be described as glass tornadoes, rotating columns of glass particles caught in powerful atmospheric vortices. These glass tornadoes stretch from the upper atmosphere down toward the planet's hidden surface, creating spiraling towers of destruction that would instantly vaporize anything caught in their path. The rotational velocities in these vortices are incredible, Dr. Martinez observes, analyzing the atmospheric dynamics data. We're measuring wind speeds inside the glass tornadoes exceeding 10,000 miles per hour. That's faster than the orbital velocity of most spacecraft. The centrifugal forces alone would tear apart any known material. You try to comprehend the scale of the forces at work in HD 189 1733b's atmosphere. The glass tornadoes you're observing are larger than entire Earth continents, rotating fast enough to generate forces that would destroy mountains. The amount of energy being released in this single storm system exceeds the total power output of human civilization by orders of magnitude. We're also seeing something that challenges our understanding of glass formation, Dr. Chen reports, studying the spectroscopic data. Some of the glass particles appear to be hollow. They're forming as bubbles or shells rather than solid fragments. The atmospheric pressure and temperature conditions are creating glass structures that shouldn't be stable under normal physics. The formation of hollow glass particles in HD 189 723b's extreme atmosphere represents a previously unknown physical phenomenon. You realize that the combination of supersonic winds, extreme temperatures, and exotic chemical reactions is creating conditions that push matter beyond the normal rules of materials science. These hollow glass structures could represent entirely new forms of matter that exist only under the most extreme conditions. Temperature readings are now exceeding our instrument's maximum range, the probe specialist announces. We're seeing temperatures above 2,400 degrees Fahrenheit, hot enough to melt platinum. The probe's thermal protection system is being pushed beyond its design limits. You watch the probe's internal temperature readings climb steadily as the external conditions become increasingly extreme. The diamond composite hull that seemed impregnable is now showing signs of thermal stress as the outside temperature approaches the melting point of the protective materials themselves. The storm's intensity continues to increase as the probe descends deeper. 197.33 atmosphere. The glass rain transforms from individual particles to what can only be described as sheets of molten glass falling through the superheated atmosphere. Some of these sheets are kilometers wide, creating curtains of liquid glass that undulate in the powerful atmospheric currents. This is unprecedented. Dr. Martinez says, her voice filled with scientific excitement despite the probe's deteriorating condition. We're witnessing the formation of glass structures on a planetary scale. Those sheets of molten glass could be forming temporary glass formations in the atmosphere. Essentially floating glass islands that form and dissolve continuously in the atmospheric currents. The concept of floating glass islands in an alien atmosphere stretches the imagination. You picture massive sheets of glass, kilometers in extent, forming and reforming in the violent winds of HD 180-9733b's atmosphere. These structures would exist for perhaps minutes or hours before being torn apart by atmospheric turbulence, only to reform elsewhere in the planet's global glass storm. We're detecting resonance frequencies in the glass formations, Dr. Chen reports. Analyzing acoustic data from the probe, the glass sheets are actually vibrating in the atmospheric winds, creating sounds that span frequencies from subsonic to ultrasonic. It's like the entire planet is singing. A song made of glass and wind and temperatures that would melt steel. The idea of HD 189,1733b as a musical instrument on a planetary scale is both beautiful and terrifying. You imagine the low-frequency harmonics generated by massive glass sheets vibrating in supersonic winds, creating acoustic phenomena that could be detected from interstellar distance. This adds another dimension to the already complex physics of glass rain worlds. Hull breach imminent. The probe specialist announces, we're seeing microfractures propagating through the diamond composite. Internal temperature rising rapidly. The glass particles are beginning to penetrate the hull. You watch with fascination and dread as the first glass fragments begin appearing inside the probe's protective shell. These particles, still moving at incredible velocities, despite penetrating the hull, ricochet around the probe's interior like tiny bullets made of superheated glass. Each impact creates sparks and damage to sensitive equipment. The probe is transmitting data about its own destruction. Dr. Chen observes, we're getting real-time information about how glass particles interact with advanced materials under extreme conditions. This destruction data is as valuable as the atmospheric observations. The probe's internal cameras show the gradual infiltration of glass particles into systems that were designed to be completely sealed. You realize you're witnessing the ultimate test of human materials science against one of the universe's most hostile environments. The fact that the probe survived even this long represents a tremendous achievement in protective technology. Signal degradation increasing, the specialist reports. Multiple systems failing due to glass particle impacts. Communication may be lost at any moment. The final minutes of Probe 2's operation provide some of the most dramatic and scientifically valuable data of the entire mission. As the probe's systems fail one by one, its sensors continue to gather information about the glass rainstorm's most extreme conditions. Temperature readings spike beyond measurement. Particle velocities exceed the instrument's ability to track. And the atmospheric dynamics reveal complexity that challenges current theoretical models. Final transmission coming through, Dr. Martinez announces. The probe is sending its complete data package before total system failure. We're getting atmospheric composition, temperature profiles, particle analysis, and electromagnetic field measurements right up until the moment of destruction. The probe's last camera image shows the interior completely filled with glowing glass fragments, the electronic systems sparking and failing as the superheated particles destroy everything they touch. Then the signal cuts to static as HD 189,733 B's glass rain claims another victim. Probe 2 destroyed. The specialist reports. Total operational time 28 minutes 43 seconds. All primary scientific objectives achieved despite early termination due to extreme conditions. The silence following the probe's destruction is filled with the weight of what you've just witnessed. Two of humanity's most advanced technological achievements have been completely destroyed by the natural forces of an alien world. Yet, their destruction has provided unprecedented insights into one of the universe's most extreme atmospheric phenomena. The data we've collected will revolutionize our understanding of exoplanetary atmospheres. Dr. Martinez says, reviewing the preliminary analysis, we've documented glass rain formation under the most extreme conditions ever observed, measured atmospheric dynamics that push the boundaries of fluid mechanics, and observed the creation of exotic glass structures that don't exist anywhere else in the known universe. You begin to appreciate the broader implications of your mission to HD 189, 733b. The glass rain phenomenon you've studied represents more than just unusual weather. It's a demonstration of how matter behaves under conditions that approach the theoretical limits of stability. Every observation contributes to humanity's understanding of physics, chemistry, and materials science under extreme conditions. There are implications for spacecraft design, materials engineering, and even our understanding of stellar evolution. Dr. Chen adds, worlds like HD 189, 1033b represent the extreme end of planetary atmospheric dynamics. Studying them helps us understand the full range of conditions that exist in the universe and prepares us for encounters with even more exotic environments. Captain Rodriguez begins preparations for the mission's final phase, deployment of a long-range atmospheric observer. Designed to study HD 189, 1733b's glass rain from a safer distance. The atmospheric observer is built for extended operation in extreme electromagnetic environments, she explains. Instead of descending into the atmosphere, it will maintain position in the planet's magnetosphere and use remote sensing to study the glass rain phenomenon over longer time periods. This final probe represents a different approach to studying HD. A 189, 1733 extreme weather. Rather than sacrificing advanced technology for close-up observations, the atmospheric observer will provide long-term data about how the glass rain phenomenon changed. You realize that understanding the temporal variations in glass rainstorms could be as important as documenting their immediate characteristics. Launch in 5 minutes, the specialist announces. The atmospheric observer is equipped with advanced spectroscopic instruments, electromagnetic field sensors, and high-resolution imaging systems designed to operate in the radiation environment around HD 187 sir. You watch as the atmospheric observer deploys from your ship and begins its journey to HD 189-17-33b's magnetosphere. Unlike the previous probes, This one isn't designed to sacrifice itself for science. It's built for long-term survival in the hostile environment around a glass rain world. Observer achieving orbital insertion. The specialist reports. All systems nominal. Beginning long-term atmospheric monitoring sequence. Oh. The atmospheric observer's first images of HD 189,733b from its orbital vantage point reveal the full scope of the glass rain phenomenon. Direct from space, you can see the planet's entire atmospheric circulation system. Massive storm fronts that span hemispheres, glass particle clouds that spiral around the planet in complex patterns, and electromagnetic activity that creates aurora-like displays on a planetary scale. Look at the atmospheric structure, Dr. Martinez says, highlighting features in the orbital imagery. We can see distinct layers of glass particle density at different altitudes. It's like the planet has multiple weather systems operating simultaneously at different atmospheric levels. The orbital perspective provides insights that couldn't be obtained from the destructive atmospheric probes. You can see how glass rainstorms form and dissipate, how they interact with the planet's day-night temperature differential, and how they're influenced by HD 189-1733b's unique orbital characteristics. We're detecting seasonal variations in the glass rain intensity, Dr. Chen reports, analyzing data from the observer. As HD 189,733b moves through its elliptical orbit, the changing distance from its star affects the atmospheric dynamics. The glass rain is actually more intense when the planet is farther from its star. Counterintuitive. This orbital variation adds another layer of complexity to the glass rain phenomenon. The intensity and characteristics of the glass storms change continuously as HD 189,1733b follows its orbit, creating a dynamic system that varies on timescales from hours to months. Understanding these variations is crucial for predicting and modeling glass rain behavior on other exoplanets. The electromagnetic signature is fascinating, Dr. Martinez observes, studying the observer's field measurements. The glass rain creates a continuous electromagnetic field that extends well beyond the planet's atmosphere. Any spacecraft approaching HD 189,733 would encounter these fields millions of kilometers before reaching the planet itself. The extended electromagnetic effects of glass rainstorms represent another hazard for potential space missions to such worlds. You realize that the dangers of glass rain planets extend far beyond their immediate atmospheric conditions. They create hostile electromagnetic environments that could affect spacecraft operations across vast distances. Over the following days, the atmospheric observer provides a comprehensive picture of HD 189,733b's glass rain cycle. The data reveals that the phenomenon is even more complex than initially thought, with multiple interconnected processes operating on different timescales and at different atmospheric levels. We're seeing evidence of glass rain cycles that operate over periods of weeks or months, Dr. Chen reports. There appear to be long-term patterns in the storm systems, essentially seasonal variations in glass rain intensity and distribution that correspond to the planet's orbital dynamics and stellar radiation variations. These long-term patterns suggest that glass rain worlds have their own version of climate, with predictable variations in atmospheric conditions that change over extended periods. Understanding these climate patterns could be crucial for planning future missions to glass rain planets and for identifying the best times to attempt atmospheric studies. The most remarkable discovery is the self-organizing behavior of the glass particle systems. Dr. Martinez adds, the particles aren't falling randomly. They form coherent structures and patterns that persist for days or weeks. It's like the atmosphere has its own intelligence, organizing the glass rain into efficient patterns for heat and energy distribution. The concept of self-organizing glass rain patterns challenges traditional understanding of atmospheric dynamics. You realize that HD 189,733b's extreme conditions create emergent behaviors in its atmospheric system. Complex patterns and structures that arise spontaneously from the interaction of simple physical processes operating under extreme conditions. There are philosophical implications to what we're observing, you comment, struck by the complexity of the patterns emerging from the apparently chaotic glass rain system. Oh, if glass particles can self-organize into coherent structures under these extreme conditions, what does that tell us about the potential for complex organization in other extreme environments? The question touches on fundamental issues about how complexity emerges from simple physical processes. AG 189 733 glass rain system demonstrates that even under the most hostile conditions imaginable, matter can organize itself into sophisticated patterns and structures. This has implications for understanding everything from the formation of planets to the potential for life in extreme environments. The long-term data is revealing that glass rain planets like HD 189,733b might actually be more stable and predictable than we initially thought, Dr. Chen observes. Despite the extreme violence of the individual storms, the overall system shows remarkable consistency over time. The chaos creates its own order. This stability within chaos represents an important insight for exoplanetary science. Glass rain worlds might appear to be completely unpredictable and hostile, but they actually operate according to consistent physical principles that create predictable long-term behaviors. This predictability could make them valuable targets for detailed scientific study. We need to expand our search for glass rain worlds, Captain Rodriguez suggests. If HD 189,733b is representative of a class of exoplanets, there could be hundreds or thousands of similar worlds in our galaxy. Each one would provide a unique laboratory for studying matter and energy under extreme conditions. The prospect of discovering many more glass rain worlds opens exciting possibilities for comparative exoplanetary science. By studying multiple worlds with similar extreme atmosphere conditions, scientists could identify the fundamental physical principles that govern glass rain formation and evolution. The atmospheric observer will continue monitoring HD 189,733b for the next several months, Dr. Martinez explains. We want to document at least one complete orbital cycle to understand how the glass rain phenomenon varies over longer time periods. This long-term data will be crucial for developing predictive models of glass rain world atmospheres. As your mission to HD 189,733b enters its final phase, you reflect on the incredible discoveries you've witnessed. What began as a study of unusual weather has revealed fundamental insights into atmospheric physics, materials science, and the behavior of matter under extreme conditions. The glass rain phenomenon represents just one example of the incredible diversity of conditions that exist on exoplanets throughout the galaxy. Every world we study teaches us something new about the universe. You observe. Watching HD 189 733B's glass storms. Safety of your observation deck. AG 189,733B shows us what happens when atmospheric dynamics operate under the most extreme conditions possible. It challenges our assumptions about what's possible and expands our understanding of how matter and energy interact. The scientific implications of your glass rain research extend far beyond planetary science. The materials created in HD 189,733B's atmosphere, the electromagnetic effects generated by glass particle storms, and the complex organizational behaviors observed in the atmospheric system all contribute to broader understanding of physics and chemistry under extreme conditions. There are practical applications too, Dr. Chen adds. The glass formations we've observed could inspire new materials technologies. The electromagnetic effects could lead to advances in power generation and storage. Even the atmospheric dynamics could inform weather prediction models and climate science. As your mission concludes, you realize that the study of glass rain worlds represents a new frontier in scientific exploration. These extreme environments push the boundaries of current understanding and provide natural laboratories for studying physical phenomena that couldn't be replicated under Earth conditions. The universe is full of wonders we're only beginning to discover, Dr. Martinez says, as the research vessel begins its journey back to Earth. Glass rain worlds, diamond planets, worlds with metal snow and ruby storms. Each discovery expands our understanding of what's possible and challenges us to develop new theories and technologies. The journey back to Earth provides time to analyze the enormous amount of data collected during your mission to HD 733B. Every measurement, every observation, every image captured during the brief lifetimes of the atmospheric probes contributes to a comprehensive picture of one of the universe's most extreme weather phenomena. The glass rain data will keep atmospheric physicists busy for years. Dr. Chen predicts that we've documented processes that operate under conditions so extreme they push matter to its theoretical limits. Understanding these processes could lead to breakthroughs in materials science, energy generation, and even our fundamental understanding of how matter behaves under extreme conditions. Your mission report becomes one of the most significant documents in the history of exoplanetary science. The detailed observations of glass rain formation, evolution, and destruction provide the first comprehensive study of extreme atmospheric dynamics on an exoplanet. The data collected will inform theoretical models and guide future missions to similar worlds throughout the galaxy. This is just the beginning, Captain Rodriguez says, as Earth comes into view after months of interstellar travel. The techniques we developed for studying HD 189-1733b can be applied to dozens of other extreme worlds. We're entering an era where we can directly study the most exotic environments in the universe. The return to Earth marks the end of your mission to the glass rain world, but it also represents the beginning of a new phase in humanity's exploration of extreme exoplanetary environments. The technologies developed for surviving glass rainstorms, the scientific insights gained from studying atmospheric dynamics under extreme conditions, and the new understanding of how matter behaves at the limits of stability will all contribute to future missions to even more exotic worlds. Future missions could study worlds where it rains liquid metals, planets with atmospheres of vaporized rock, or worlds where the atmospheric pressure is so extreme that familiar matter takes on entirely new forms. Dr. Martinez speculates, each extreme world we study expands the boundaries of known physics and chemistry. As you prepare to return to normal life on Earth, you carry with you the memory of witnessing one of the universe's most incredible phenomena, the glass rain of HD. Rain 1733b represents a demonstration of nature's power to create conditions so extreme they challenge human imagination. Yet, through careful study and technological innovation, humanity has managed to peer into this alien world and extract scientific knowledge that expands our understanding of the universe. Your journey to study the strange science of planets that rain glass has revealed that the universe is far more diverse and extreme than previously imagined. Every world offers unique conditions that test the limits of physical law and provide opportunities for discoveries that could revolutionize science and technology. The glass rain worlds are just the beginning of humanity's exploration into the most exotic environments the cosmos has to offer. The data streams back to Earth, carrying with them the secrets of glass rain formation, atmospheric dynamics under extreme conditions, and the behavior of matter pushed to its theoretical limits. These insights will inspire new technologies, inform new theories, and guide future missions to even more extreme worlds throughout the galaxy. Your mission to HD 189733b represents a milestone in humanity's quest to understand the incredible diversity and complexity of planetary atmospheres throughout the universe.